Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and today we are going to discuss about the synthesis and design of inorganic materials under the subject of advanced inorganic material chemistry. So far, we have discussed some of the important points in solid state reaction or shake and bake methods. So, we have studied the nucleation and growth, epitaxy and autopotaxy, and then we will discuss the some of the spinal product layers separating magnesium oxide and aluminium oxide reactant grains. Today, we are going to discuss some of the synthesis and processing behind the magnesium aluminium oxide. In order to preserve local neutrality during reaction and throughout the product, it is necessary that for every 3 magnesium ion Mg2 plus ions that diffuse to the right hand interface, 2 aluminium Al3 plus ions must diffuse to the left hand interface. The reaction that occurs at interface may be written ideally as follows. Here is actually the interface for magnesium oxide and magnesium aluminium oxide, while this is for the interface of magnesium aluminium oxide and aluminium oxide, and the net reaction would be like this one, in which 4 magnesium oxide reacted with the aluminium oxide and they change into magnesium aluminium oxide. The overall reaction from which we see that the right hand interface should move 3 times as quickly as left hand interface. In cases where reactant and product are of a different color, it may be possible in carefully designed experiments to observe some of the visually displacement of the interfaces. This is known as Kirkendall effect. The spinal formation reaction is particularly slow because ions, for example magnesium Mg2 plus ion and aluminium 3 plus ions, diffuse very slowly. Typically, heating for 1 week at about 1500 degrees Celsius would be required to form a fairly pure spinal product. Defects in both reactants and the products are required, particularly vacant sites for adjacent ions to hop into. High temperatures are therefore required so that ions have sufficient thermal energy to occasionally hop out of the one site into adjacent vacancy or interstitial site. Consequently, it can be difficult for solid state reactions to proceed to completion once the remaining reactants are well separated from each other. One important way to accelerate reactions is to grind the partially reacted mixtures so as to break up reaction product interfaces and bring fresh reactant surfaces into contact. So this is supposed to be the best way for the synthesis of interfaces different. One important way to accelerate reactions is actually of the grinding the partially reacted mixtures. We should have to put back the reacting mixtures and we should have to grind it more precisely so as to break up the reactant product interfaces and to bring fresh reactants surfaces into the contact. Another way is if gas or liquid phase assisted transport of matter can occur and bring reactants together without the need for long range solid state diffusion. A small amount of liquid or gaseous transporting agent may be very effective in enhancing reaction rates. So far, we have studied the two different ways to accelerate the reactions. The first one is actually the grinding the partially reacted mixtures so as to break up the reactant product interfaces and bring the fresh reactant surfaces into the contact. So it will enhance the reaction chances between the reactant and products. Another way was the if a gas or liquid phase assisted transport of matter can occur and bring reactants together without the need for the long range solid state diffusion. A small amount of liquid or gaseous transporting agent may be very effective in enhancing reaction rates. Now let's talk about the practical considerations and some examples of solid state reactions. The problems associated with spinal synthesis by solid state reactions are particularly difficult since both reagents are were the magnesium oxide and aluminum oxide are very stable and they are supposed to be quite inert and non-reactive solids. The magnesium oxide and aluminum are supposed to be the most stable, inert, and the non-reactive solids. Solid state reactions may be easier if one or more of the starting materials is chemically reactive and contain ions that can diffuse easily. Other problems may arise, however, such as potential loss of reactants by evaporation. Evaporation, for example, alkali metal oxides that may be the titanium oxide, lead oxide, and bismuth oxide, mercury oxide, or sometime reactivity towards the container, if for example transition metal containing materials, because the containers where we place the different reactors of course sometime bears many transition metals sometime as impurity, so we they may have affinity for the reactions for these kind of materials, for these kind of transition metals. So we should have to be quite careful for the choosing of the container where we are going to react the different reactants. It should be non-reactive in nature, and there are many metals in the periodic table that are quite unreactive towards many reactants. With care and attention to synthesis procedures, these problems can usually be avoided, and these problems can also be addressed properly. There are four main issues for consideration in planning a solid state reaction, that is actually the choice of starting materials, mixing methods, container, and heat treatment conditions. So these are the four major issues uh, which should be under the consideration in while planning a solid state reaction. So the first one is the choice of starting materials or the starting materials. Ideal starting materials should be of accurately known stoichiometry. and it should be pure and reactive. Problems with stoichiometry and purity can arise if the reactants are sensitive to water or sometimes carbon dioxide, which is present extensively in the atmosphere, or sometimes contain transition elements in uncertain or mixed valence states. Reagents may need to be dried at a temperature found by trial and error and subsequently kept in a desiccator. Desiccator would help us to remove uh, any kind of humidity or any kind of water vapors if present in the reaction mixtures or in the reagents. For oxide synthesis, it can be useful to use oxysalt reagents such as carbonates, acetates, or nitrates. Since uh, these decompose during the initial stages of reaction on heating. This decomposition step may decrease greatly and the particle size of the reagent increase its surface area and therefore increases potential reactivity. In addition to this, evolution of gases during the decomposition can also be helpful to mix the solid reactants. So these are the different behavior of starting materials while performing the solid state reactions. uh, as I have told you that the gases which is evolved while heating or sometimes by the process of decomposition, it can also be helpful, quite helpful in some of the solid state reactions to facilitate the reaction, and that would be helpful sometime to make the pure inorganic materials. The second one is the after starting materials is the mixing of reactants. For solid state reactions, it is essential to bring particles of reactants into contact. This is actually facilitated by increasing the surface area of the reactants. Now, it is very important to learn about the mixing of reactants. Samples are somehow therefore are mixed and mild. This can be done manually using a pistol mortar, and the pistol motor may be agate mortars, and pistols are sometimes useful since they are non-porous in nature, and they are easy to clean, and it sometimes should not contaminate the samples. So that's why we encourage to use the pistol mortar for the best mixing of the reactants. They are also There are also various labor saving mechanical mixing techniques such as ball milling, in which the mixture of reactants is placed inside a rotating container together with a number of balls of, for example, agate. So this is also can be used actually for the mixing of reactants. Both methods can be used extensively, but in laboratories, the most important one is the first one, which was the pistol mortar grinding. Due to its non-porous behavior and non-reactivity towards the samples and easy clean behavior. There are the container is uh, then rotated for a period of time, for example 3 to 24 hours, and the effect of the tumbling motion with the agate balls is to reduce the average particle size of the reactants in addition to achieving an intimate mixture. High energy milling is sometimes possible in planetary ball mills, which are actually rotated at very high speed. While the mixing and the milling processes are carried out rapidly and effectively, there is a danger of contamination from the milling media. To facilitate mixing by whatever method, a liquid such as water or an organic liquid is often added and then needs to be removed by drying at the end of the mixing stage. So the third one is the container after starting materials and mixing of reactants. Now let's talk about the third, which is the container. If the atmospheric sensitivity of the desired product phase is not a problem, the reaction mixture can simply be heated in air in a furnace in a suitable container. So it is very important to first we should have to know about the sample behavior, sample sensitivity. If it is not a problem, the reaction mixture can easily be heated in air. Prime consideration for a container is that it should not react with the sample, because if it is reacted with the sample, then we may did not get the desired product, because the reactants may react with some of the metals ions or some of the transition metal ions present in the container, and they form their different amalgams or sometime compounds that would not help us to uh, proceed for the exact products that we want to study. So prime consideration is actually for the container is that it should not react with the sample, it should be inert in nature, and frequently used inert containers for oxides are boards or crucibles of platinum pt, but platinum have reactivity towards with lithium oxide and barium oxide and some of the transition metal oxides. So if we have such kind of reactants in our reactant mixture, then we should better to avoid from platinum containers. The second one is the gold container. Gold, but its melting temperature is about 1063 degrees Celsius. It actually places an upper limit on the reaction temperatures that may be used. However, gold is generally more inert and useful than platinum because of their non-reactivity towards the different reaction mixtures. Aluminium oxide, Al2O3. The third one is aluminium oxide. It is actually a high purity alumina, is inert and high melting, but nevertheless contamination from the reactants may occur. So it may sometime react alumina, sometime may react with some of the reactants, which causes severe contaminations although it is quite inert and have high melting point. So we do not have an upper limit like in gold, which was about 1063 degrees Celsius. Silicon oxide, AlSiO2 glass. The crucibles of silicon dioxide glass can withstand temperature up to 1200 degrees Celsius before the glass softens and starts to de-vitrify. The oxides of alkali metals in particular are reactive towards silicon dioxide. So silicon dioxide however have high melting point. It can stand up to 1200 degrees Celsius, which is higher than the gold, and it is supposed to be quite reactive. But if we are using the oxides of alkali metals in particular, so these are reactive towards silicon dioxide. So if we are using the alkali metals oxide, the silicon dioxide glass should be ruled out. We do not use silicon dioxide because of the reactivity towards alkali metal oxides. The fifth one is actually the graphite crucibles, which are commonly used as containers for the synthesis of sulfides, other chalcogenides, and nitrides. Graphite crucibles are quite helpful for the synthesis of sulfides and nitrides and chalcogenides. So these are the different containers that may be used after the mixing of reactants, and we should have to use carefully container for different reactant materials, because different containers may have different reactivity or inertness or sensitivity towards different reaction mixtures. So it is very important to choose the correct container for the correct reaction mixture. So far we have studied the three parameters for the solid state reactions that we need to adopt. This is actually the practical consideration, and we will discuss some of the example of solid state reactions. The first one was the starting materials. We should have to choose the ideal starting materials and correct stoichiometric amounts, while the second one was the mixing of reactants, which is very very important. We should have to adopt the particular method for the mixing of reactants that would be helpful for the better results, because if the mixing procedure interfere in the purity of the reagents, then it will leads to the improper results, and it will leads to the impure products. And the third one was the container. We should have to choose the different we should have to choose the specific container that would be used for the specific reacting mixtures to synthesize the different compounds. The fourth one is the firing schedule. The heating schedule should be designed to create a cause smooth decomposition of any oxysalt reagents without the excessive frothing, melting, or leakage of the reagent from the container. The B, it should avoid melting, and in particular volatilization of one or more of the reagents. And the third one, which is the C, apply temperatures at which reagents react together on a reasonable time scale. The reasonable time scale should vary from 12 to 24 hours. Reactants Reactions may be carried out in air, or if a tube furnace is available, a range of controllable atmospheres may be used. Alternatively, sealed ampoules of silica glass or precious metals may be used to prevent loss of volatile reagents or atmospheric attack. For known materials, there may be recipes in the literature uh, detailing the appropriate reaction conditions, but for the attempt synthesis of new materials, a trial and error approach is usually needed. That would be all for this lecture. Thank you very much.